Okay, Chapter 6 in your ALEKS integrated textbook is the place to go to look up examples of factoring polynomials. Now, we could factor polynomials for a month. This is one of those algebra techniques that is the stereotypical, when am I ever going to do this in real life kind of thing. Chances are you're not going to do this in real life, except in the event that you're taking classes like other math or physics where expressions have been prepared for you in a way that will require factoring in order to simplify something. But when you're factoring, remember the second layer of practice. You're not just learning how to factor, you're learning to recognize patterns. That's really the important issue that's going on behind the scenes. Now, you know how to multiply polynomials out. Factoring is just reversing the process. So here's a polynomial, x squared plus 13x plus 22. And we're asked to factor it. What we're doing is we're saying, gosh, it would be nice to know what two binomials were multiplied together to produce this polynomial. And so we can take a crazy guess that we probably had a multiplication like that, x plus or minus this times x plus or minus that. Now, the pattern that we're going to look for is how can we ensure that we would develop the first term with the x squared and the last term with the constant 22 while at the same time producing the 13x. So, well, the first part's easy. It's very likely that both of these binomials led off with x. And then on the back end, you got some choices. Maybe there was a 22 and a 1, or a 1 and a 22, or what other numbers multiply together to make 22? How about 11 and 2, or 2 and 11, right? So there's a whole bunch of different options of the two constants that can go there and there. Here's where the pattern comes in. Since you know how to multiply this out, you have to pick the numbers from here that would result in the 13x when you added the terms together that would have pop up during the multiplication, right? So just as an example, over here on the side, let's say it was x plus 22 times x plus 1. Let's say that was the factored form, right? Well, when we multiply that out, we would certainly get the x squared. We would certainly get the 22 as the front two ends. But in the cross terms, we would get 22x and 1x. Sorry, had to squeeze that in there. And so the net there would be x squared plus 23x plus 22. Well, that's not what we have. We have x squared plus 13x. So I think we can rule out those two, because I actually just tried that. By symmetry, we can rule out that. So now we're down to 11 and 2, or 2 and 11. And in this case, either one of them is going to work. Let's try it like this. So when we multiply those two binomials, the leading x times the leading x will produce the x squared. The trailing 11 times the trailing 2 will get us the 22. And then the cross terms, 11x and 2x added together will produce the 13x. And so that is the correct factored form, written without all the clutter, just for completeness. Now, down on the second part of the page, there's a polynomial that's a fourth order polynomial. Oh my goodness, that's going to be twice as hard at least, right? Well, no, because again, this is all about pattern matching and understanding that we are trying to just reverse multiplication of two binomials. So some multiplication resulted in this, and we were trying to break it back apart into the things that produced it. So the leading term here is x to the fourth, and the middle term has x squareds. And remember, the middle term will get produced by adding two cross terms that would occur during multiplication. So rather than leading with x and x, how could we make that x to the fourth? Well, let's suppose we had x squared and x squared. as the leading parts. When we started multiplying that out, that would certainly produce an x to the fourth. On the tail end of this, we needed negative 36. Now, negative 36, that's going to have a ton of potential factors in its breakdown. So we could have 36 and 1. We could have 12 and 3. We could have 6 and 6. We could have 9 and 4, right? There's all sorts of combinations, and that's not even getting into which one's positive and which one's negative or vice versa, okay? So I'm not going to make a big, long list. I think we can rule out 36 and 1 regardless of the minus signs because those cross terms would never lead to that 5. What we're looking for is two constants that if we added them up as coefficients of the cross term in their plus or minus forms, we could produce a 5. So when we're thinking through 36 and 1, does any combination of those produce a 5? No. 12 and 3, can we additively or subtraction-wise produce a 5? No. 6 and 6? No. 9 and 4? Now we've got something. So I think we're going to follow our nose and put in a 9 and a 4 there. And now we just have to decide which one's positive and which one's negative. So we could have positive, negative, or negative, positive, and now we just have to decide which one of those would produce the cross term of positive 5x squared. Since we have a positive sign here, we need the larger of the two mini terms that go into producing that during the multiplication being the positive one. And so how about plus 9 and minus 4? So x squared times x squared, bingo, there's our x to the fourth. Positive 9 times negative 4, negative 36, bingo. And the cross terms, 9x squared minus 4x squared would be positive 5x squared. And so there we go. If you don't believe me, put in the plus and the minus and the plus instead and carry out that multiplication, and the middle term will be negative 5x squared instead. So we've got it right.